Hello, good evening. Am I audible?
Yes, sir, you are audible.
Okay. So anyone here who attended this session earlier also, or all are new? Okay. So it is better. Let me introduce me again. That I am Suman Sadhu. I am a PhD second year student from IIC Bangalore, and in this live session, I will actually solve the few of the great previous year questions and also try to cover the concept related to those questions. So if you people have any doubt regarding those questions or regarding those concepts that will be covered, so you can ask anytime. You can also even interrupt me in between. So so let's move to solve the first question of today. uh, okay. Uh, Screen is visible to everyone, right?
Yes, sir.
Yes. Okay, so this is the question number 44 of GATE 2016 Metallurgical Engineering. The question is the density and corresponding crystallinity of two polypropylene material are given below. So for the first case, the density is 904 and the crystallinity is 62.8 percentage. And the second case, the density is 895 and the crystallinity is 54.4 percentage. The density of the totally amorphous polypropylene in kg per meter cube is option A 723, option B 841, option C 905, and option D 956. So let us solve these questions. Before that, anyone has any idea or anyone can try to answer how to proceed? Hello. Okay. So let us solve this question. So you have to calculate the density of the totally amorphous polypropylene. So in case of polymer, what happens that uh, arrange, uh, arrangement of the that polymer linkage. So that might be a amorphous kind of, or it might be a crystalline. So crystallinity basically refers to the degree of the ordering in the structure or degree of the regular order present that in the structure. So in case of polymer, it might happens that the polymer might be like a random kind of nature, or it might be arranged in a crystalline fashion. So regular arrangement may also be there. So or also it may be a mixed kind of thing. Let's say this is a polymer. Somewhere it is arranged in a regular manner. Somewhere it is amorphous kind of. So depending of the percentage of the crystallinity, its density will also vary. So that is why the density is different when the crystallinity percentage is changing. So to solve these questions, so first let us consider that this is a polymer. So let's say that this fraction uh, is a crystalline part. Okay, for the simplicity, let's draw here. So let's say this part is the crystalline part, and this part is the amorphous part. So this is the crystalline. Okay, so let's say the total volume of the sample is total volume Vs, total mass is Ms, and the density is rho s. And let's say this is the crystalline part, and the volume of this crystalline part is so volume of crystalline is Vc, mass of crystalline part is Mc, and density is, let's say, rho c. Similarly, assume that the volume of the amorphous part is Va, mass is Ma, and density is rho a. Now, what is the percentage of crystallinity? Is i- the percentage of crystallinity, or the mass is also called mass crystallinity, is given by mass crystallinity. Percentage of mass crystallinity is given by the mass of the crystalline part divided by the total mass of the sample. Right. So, in terms of density, we can write it as rho c to Vc rho s into Vs. So now, in order to express this equation in terms of the density only, we have to find out the what the ratio of the Vc by Vs. So now, in order to find this, let us see that we can write that the total mass of this sample, total mass of the sample can be written as the summation of the mass of the crystalline part plus mass of the amorphous part. Similarly, the total volume also can be written as volume Vs is equal to volume of the crystalline part plus volume of the amorphous part. Now, if we uh, write this equation in terms of the density and volume, then we can write rho s Vs is equal to rho c Vc plus rho a Va. Now we have to find the ratio of Vc by Vs, right? So for that, we have to uh, replace VA term in the terms of VS and VC. So if we replace VA, sorry, this is rho S VS is equal to rho C VC plus rho A. VA will be VS minus VC. So from this equation we can get VA is equal to VS minus VC. So now we can write this is rho S VS, rho S VS. This rho A VA we can take in this side, rho A VA VS, and let's say this is rho A VC, rho C VC minus rho A VC. Okay, so now we can take VS common from here, so it will be rho S minus rho A is equal to, we can also take common VC here, and then it will be rho C minus rho A. So now we can write, we can get the ratio, it is VS by VC is equal to rho C minus rho A divided by rho S minus rho A. Now the percentage of mass crystallinity was rho C by rho C by rho S, rho C by rho S into that ratio. The ratio is VC by VS. So VC by VS is opposite to this ratio. That is VC by VS is rho S minus rho A divided by rho C minus rho A. So this is the formula for the percentage of the mass crystallinity. So we have derived this formula. Now we can understand that how this formula is coming. So to solve this question, you can also remember this formula directly, and you can approach this question easily using this formula also. So anyone has any doubt till now how we got this relationship? Okay, okay. Okay, then now let us see that what are the value those are given to us. So the density of the sample, that is rho s for one case is given, rho s1 and rho s2 is given. We have to calculate the density of the totally amorphous polypropylene. That is, we have to calculate the rho A, right? So now uh, let us write the equations then. So from this set of data we'll get one equation, and from this set of data we'll get the another equation. So now let us see. So in this case the crystallinity is 62.8 percentage, and the density of the sample is 904. So we can write equation 1 as 62.8% is equal to density of the sample was given as 904. uh, Before that rho C term is there, so rho C into 904 minus rho A. So you don't know the value of rho C and rho A, I'm writing in terms of rho C and rho A only. Now rho S also we know, that is 904 into rho C minus rho A. We have to find out the value of the rho A, right? So this is the equation 1. Equation 2 will be 54.4% of crystallinity is there, and the density is 895. Okay, sorry, there is a mistake. If I write in the terms of percentage, then you have to multiply it by 100. Or if you are writing in the terms of fraction, then you have to it will be like this ratio only. So it will be a fraction. Okay, so from the second equation we get 54.4 by 100 is equal to rho C into 895 minus rho A divided by 895 into rho C minus rho A. This is the equation 2. Now, if we divide equation 1 by equation 2, we will get uh, to solve these questions. If you remember this formula only, then you can easily approach from this part only. I just derived this formula just to show that how this formula is actually coming. Otherwise, if I just write this formula directly, then it will be difficult to understand that how this formula is it comes and from where I am using it, right? So you can use this formula directly. That is a percentage of mass crystallinity. This formula you can use directly to solve this question. Okay. Uh, Anyone has any other doubt, or should I move? Okay. Uh, okay. So what the question said that we have to determine the density of the total amorphous polypropylene, and the density of the samples are given, right? So what happens is, like metal or this kind of structure are mostly crystalline. Their regular arrangement is there, but in case of polymer, there it may be arranged haphazardly or randomly, or it may arrange in the regular pattern. So if it arrange like this randomly, then you can say that this is the amorphous. This is the amorphous uh, uh, polymer or amorphous polypropylene. If it is arranged in this crystalline form, uh, if it is arranged like this in a regular arrangement, then you can say it totally crystalline. So in case of polymer, this arrangement you can add different curing process, and these things are there. I am not want to go in these details of this, and also I have not much idea about the polymer. So just to give a idea that what are the different structure of polymers. So this random structure is basically amorphous, and this regular kind of arrangement is a crystalline part. Now in reality, what it may happen is that some part of this polymer is crystalline now, or some part may be randomly oriented. So this part is amorphous, right? So as you can see, let's say okay, I'm drawing here. Let's say this is a crystalline polymer. If it is arranged regularly like this, and this is the amorphous polymer, let's say. Let's say it is arranged in a regular randomly. Now you can see from these two schematic that whose density is higher, the totally crystalline polymer or the amorphous polymer. You can just see the schematic and just uh, get an idea that here that it is a very closely spacing, and it is arranged in a regular kind of fashion, and the spacing is also very small. So in this case, the totally crystalline polymer will have higher density, and totally amorphous polymer will have a lower density. So that is why you can see here that the density, uh, as the percentage of crystallinity is increasing, the density is higher. As it is decreasing, the density also decreases. So now uh, from this, just seeing this question, can you means these are the given option to you, right? So just seeing this question, can you just omit out any two option from here? Because it is our that totally amorphous, what will be the density? So for totally amorphous, the density should be less, right? Less than this part, this two. I understand up to this part. Yes, exactly. Because that you can see that the crystallinity is 62.8, and for this the density is 904. So now totally amorphous means the crystal percentage of crystallinity is 0. So that means its density should be less than this two value. So directly you can cross out these two options from here, because the density cannot be higher than the crystalline, that when the crystallinity is 62.8 or 54.4. For totally amorphous polymer, the density should be lower. So our answer should be between these two options, right? So now for this we have to calculate, and as I mentioned here, that in reality it may happen some part of the polymer is crystalline, or it may happen that some part may be amorphous. So we have okay, so we have basically assumed that the total volume is Vs, total mass is Ms. That means total mass of this polymer block. Let's say I have taken a polymer block, this one. So total mass of this block is Ms, and let's say this part is the crystalline part. This regular arrangement part is the crystalline part. Volume or mass of this part is, let's say, uh, Vc is the volume, and mass is, let's say, Mc, and the density is rho c. And this, let's say, the other part are arranged randomly, and other part are uh, amorphous of this uh, polymer block. So for this, let's say the volume is Va, volume of this part is Va, and mass of this amorphous part is Ma, and the density is rho a. Now you can write the total mass as Ms is equal to Mc plus Ma, right? It is okay up to this?
Yes, sir.
Okay. So and also we can write volume, total volume as V of the crystalline part plus V of the amorphous part. That means total volume of this block we can write as a summation of this part. Let's say this is the crystalline part, and the other part, that is the amorphous part. Total volume we can write like this. So now if you uh, write this total mass in terms of the density and the volume, you will get this rho s vs is equal to rho c vc plus rho a va. Now if you substitute this va term in terms of vs and vc in this equation, you will get this equation, because as we have defined that percentage of mass crystallinity is mass of the crystalline part divided by the mass of the total sample. So we need to find out the ratio of Vc by Vs in order to write this equation in terms of density only, because only density is given to us. That volume or volume fraction or volume is not given to us, right? So we have to write this equation in terms of the density only. So that's why we have find out the ratio of Vs by Vc, or you can write that Vc by Vs will be just opposite to this ratio. So if we write that Vc by Vs, it will be rho s minus rho a by rho c minus rho a. Now if you simply just put this value here, rho c by rho s it was there, and then Vc by Vs, this value is this one, rho s minus rho a into rho c minus rho a. So now so this is the formula. From this formula you can derive the percentage of mass crystallinity, right? So if you don't know the derivation of this process up to this, if you just remember this formula, you will be able to solve this question. Just to show that how this formula is coming, how the derivation is coming, that's why I explained this part. that but if you remember this formula, it will be, you can solve this question easily. But it is better to understand this concept, so that any kind of problem you can just deal with it. It may happens that in other question, it may not be given in the terms of density only. There might be that some mass is given, or volume can also be given. So in this case, you can just play with the equation and you can find out, right? So it is okay up to this.
Yes,
Chintu,
sir.
have you any doubt?
No, sir.
Okay. Okay. So should I move further then? Okay. So now just given value, from the given value, we have got these two equation, right? So in one case, the crystallinity percentage of crystallinity was 62.8. So this mass crystallinity, that was 62.8 by 100. It was given, and then it is rho c. Then rho c, we don't know the rho c value, so we just simply wrote rho c here. And rho s was given, that is the density of the sample. It was given 904. So density of the sample was given 904 minus rho a, that is a density of the totally amorphous part, or totally amorphous polymer. So from this way we can get these two equation, and this is the second equation. So now if we simply just divide equation 1 by the equation 2, we will get that in the left hand side it will be 62.8 divided by 54.4, and the right hand side it will be rho c into 904 minus rho a divided by the 904 into rho c minus rho a. So this whole part will be divided by this one, this rho c 895 minus rho a divided by 895 rho c minus rho a, right? So now rho c and rho c will cancel out, and this rho c minus rho a will also cancel out. So what we will have, 904 minus rho a divided by this term 895 minus rho a, and this term is there in the below, that is here, and this will go up. So 895 will be here, and in this side it is 62.8 by 54.4. Now let us simply arrange this equation in order to find the value of rho a. We have to find out the value of the rho a. We have to find out, right? That is the density of the totally amorphous part. So now let's write the equation here. Simplify this equation. So can anyone calculate this ratio and just let me know? This 62.8 divided by 54.4. How much it is coming?
1.154.
Okay. So this is coming 1.154, right?
Yes.
Okay. Okay. Let's say it is 1.15, and then if we just simplify this equation, we'll get 904 into 1.15 to 895 minus rho a is equal to 895 to 904 minus rho a. Now let us write 904, sorry, into 1.15 to 895 minus 904 into 1.15 rho a is equal to 895 into 904 minus 895 rho a. So now if I bring this rho a term in this side, it will be 895 minus 904 into 1.15 rho A will be equal to 895 into 904 minus, we are bringing this one to this side, so it will be 904 into 1.15 into 895. So now, sorry, so what will be the rho A? Rho A will be this value. Can anyone calculate this part? Okay, I'm just first writing and then we calculate. 904 into 1 minus 1.15. I just took the common of this thing, and in the new denominator, this part will be there. That is 895 minus 904 into 1.15. So what is this value is coming? How much? Everyone has calculator? Okay, 840. Okay, 840.45, right? Everyone got this? 2 point. Everyone got this value? Okay, you got 839.29. Okay, let me check once. 895 into 904. Okay, if you take this as 1.154, then you will get 840.6. If you take it is 1.15 only, if you just take up to two digit, I think you will get 839.29. So that is fine. So nearby only. Okay, so your question is, it is given percentage of crystallinity, you consider its mass crystallinity. Okay, crystallinity is basically defined in terms of the mass crystallinity only. So volume is not a way to define this thing, that percentage. But in other question, it may happens that the crystallinity percentage is given, and let's say in the place of density, the mass is given or the volume may be given. But always the definition of crystallinity is percentage in terms of the mass crystallinity. That is the mass of the crystalline part divided by the mass of the total sample. So that's why it is considered as mass crystallinity, and then we have derived this from that. Okay. Okay, so we got around 840.4 or 6. That will a few decimal point you will get here and there because of the calculation little bit how much decimal you are taking. So basically that answer is option B, 841, right? So in this question, just seeing the question, you can cross out uh, these two option. So you have left these two options. Now it is become easier, right? Just to check whether you are getting correct answer or not. So you will be much more confident. if you get this answer. Okay, so anyone has any doubt up to this? Should I move to the next question?
Yes, sir.
Okay, okay. This is the question number 15 of GATE 2016 Metallurgical Engineering. Uh, which of the following cooling curves shown in the schematic is an eutectoid in an eutectoid steel will produce 50% magnetic structure? So these cooling curves and the transformation curve is showing here that cooling and the option are given. Option A is P, option B is Q, option C is R, and option D is S. So anyone want to approach how to solve this? Instead of two polypropylene, if they give one ethane and polypropylene, then is the same formula is suitable. Okay, in that case, actually, you have the mixture of two different polymer, right? So in that case, that means it is not a kind of composite in or mixture, right? It is a same polypropylene, uh, uh, but some part is crystalline and some part of is amorphous. But in case of polypropylene and one ethene, then you will have a different density of the sample itself. Then rho s will be different depending on this thing. So in that case, you have to just consider that means average density kind of thing. Or this question is kind of different. And what you are asking, it is a kind of mixture of two different polymer, and then uh, average density and mass, how it will be there. This is a different, but it is also a kind of similar thing. You can consider that this two if you consider this two polypropylene also means, let's say this part is I have crystalline, but I think approach you can use the same approach also, like what you were saying. Let's say one part is the polypropylene and part is ethylene. So in this way you can also use the same approach. Let's say this is a block and the volume of this part is V polypropylene and volume of this is V ethylene. So in this way, but this is a kind of mixture of these two different polymer, right? This you are asking, right? Yes. So in this way also you can use the same approach, like as we consider that volume, total volume is the volume of this part and volume of this part. So this in this case also you can use this same approach. So then you have to find out this means according to the problem. Then you have to approach this. What are the equations that you have to just play with the equation? But approach you can use the same. It is kind of a mixture of these two things. In our question, it was a mixture of the crystalline part and other part was the amorphous part. But approach you can use the same. If it is asking that percentage of the each fraction of each polymer, then you can use the same approach. Got it? Okay. Okay. Now let's move into the next question. So here we have to calculate, or we have to see which cooling curves will produce 50% magnetic structure, right? So it is an eutectoid steel. So eutectoid steel means like this is, let's say this is the phase diagram. So eutectoid means this steel. This is the AC1. This line is given here. Above AC1 it is austenite or gamma, and below it will transform to the perlite. Now, if you cool from this part, so from this part you are cooling. If you cool equilibrium, do the equilibrium cooling up to the room temperature, you will get the equilibrium fraction, phase fraction, and as it is a detector still, you will get 100% perlite. But if you follow different cooling rates, your that percentage or different phases you will obtain will be different. That percentage will also may vary, and also the morphology also may vary. So in, let's say, this in the fast cooling curve, let us first consider the all the cooling curves one by one. So let's say this is the fast cooling curve. It is basically cooling from the austenite region to the directly it is coming to the below the ms temperature. It is not touching any of this C curve, right? By the way, what this C curves denotes, anyone? What is this C curve means? What it is? What is the significance or what it is showing? C curve is not a composition. You can see in the y-axis it is temperature, x-axis it is time, and these are the C curve. What the transformation? Yes, that it is basically showing the percentage of the transformation. How much percentage of that transformation is occurred. So how you will get its C curve? Anyone has any idea how this C type of curves will get? And why it is the shape of this curve is C, in the shape of C type? Why it is not in the other shape? Okay. Okay, now first solve this question, then I will discuss these things also, while the shape is C and how you will get the C type of curves. Okay, so now first solve this question first. So this first C curve is basically showing the transformation start curve, and the this C curve is showing the transformation of the transformation end curve. C curves basically showing how much transformation you have at a certain temperature and time. For a certain temperature and time, how much percentage of those phase will you will get. Basically, this idea will get from the CCT diagram or TTT diagram. So now this dotted line is basically showing the 50% transformation curve, right? And this part is known as the nose of the C curve. This is the nose of the C curve. Now, above the nose, we will get perlitic morphology, and below the nose, we will get benitic morphology. What is the difference between the perlite and benite? Anyone? Both are mixture of ferrite and cementite, right? But what is the difference? Okay, microstructure, right? But what kind of difference is there? Like, what is the difference in the microstructure? Anyone else? Precipitate, precipitate of cementite occurs, right? Basically, the difference is yes, right. That microstructural difference is there. Also, we will get the precipitate of cementite, but the main difference is that the morphology of the yes, morphology of the ferrite phase, that morphology are different. In perlite, you will get lamellar kind of. Let's say this is the sorry. Let's say this is the alpha, and this is the cementite alpha cementite. This kind of thing will get. But in case of benite, what you are doing? You are quenching or you are cooling at a very fast rate. So what happens that morphology of the Alpha is basically elongated. This benite shape is kind of, initially it is supersaturated with carbon. Okay, but this is not a equilibrium condition, so carbon should have precipitate out. That's why uh, carbon can precipitate either inside this benite shape, or it also can precipitate outside depending on which temperature you are aging. So this part also you can understand from this CCT diagram. So let us move further. So before that, first anyone want to tell that if we follow the S cooling curve, let's say this cooling curve, what will be the final microstructure? Yes, martensite, right? Yes, but you cannot tell it will be only martensite, because you don't know that it will transform to 100% martensite or not. There might be some amount of written austenite also, right? So this will give you martensite plus written austenite. Okay, so that percentage of written austenite vary with the different factors, what are the composition you are having and all. So now let us consider the second cooling curve, that is this one, cooling curve Q. So what we are doing here, from the austenitic region, we are cooling at a very fast rate, so that it will not or it is not touching this nose or any of the transformation start line. So that means here the transformation will not start. Up to this also it will be written austenite. Then also this written austenite is holded at this particular temperature for a certain period of time. Now, as soon as it is touching this curve, that means transformation is starting from this point, and we are holding it further. That means, at sorry, let's say when we quench that, it will be a mixture of lithium austenite and supersaturated alpha. So now, when we are holding it, what is happening at this point? The carbon started precipitating out. So this, depending on this temperature, that morphology might be different. Like this, if this temperature is above 350, then you will get precipitation at the boundary of this alpha, that is upper benite. And if this is below 350, then you will get lower benite, that is alpha, and precipitation will be inside this supersaturated alpha only, right? So at this point, your transformation is starting, then it is going further, then it is touching this point, that is the 50% transformation, and then we are quenching it. So in this, if we follow this cooling curve, what microstructure will get? Anyone? What microstructure will get? At least you can try. 50% benite
The
plus,
benite.
yes, plus lithium austenite plus martensite. Okay, yes, you are right. So as it is touching this transformation curve below the nose, so it will start forming benite from here, and then it is touching the 50% transformation line. So that means up to this point 50% transformation of benite is occurred. Then we are quenching it. So up at this point we have 50% benite plus written austenite, right? Now when we are quenching it, so those written austenite, some parts of this written austenite will transform into the martensite, or there might be some percentage of the written austenite also may left. So the final microstructure will be 50% benite plus lithium austenite plus martensite, right? So we got our answer, by the way, that is 50% benite, that Q cooling curve will form. But to understand this CCT curve in much better way, can anyone try to answer if we follow this R curve? R cooling curve, what will be the final microstructure? Now we have understood, right, how we are getting different kind of microstructure depending on the different cooling rates. That composition of this still is same. The composition is not varying. It is a eutectoid composition. But as you are following different cooling rate or you are doing different heat treatment, different kind of microstructure you are getting. Right? Like in case of AS, you are getting martensite plus lithium austenite. In case of Q, you are getting 50% benite, lithium austenite, and martensite. So in case of R, what will be the final microstructure? Perlite plus martensite. Yes. So this is also touching this start curve here. So at this point, the transformation will start. Then it is touching here that 50% transformation, and then it is basically quenching. Uh, so up to this point, there will be a perlite formation that around 50% perlite, mostly 50% perlite will produce, and the rest of the part will be lithium austenite. Okay, so this lithium austenite, when it is coming below the MS temperature, some parts of this lithium austenite will transform into the martensite. So so in the final microstructure, we'll get around 50% perlite plus martensite plus lithium austenite. And what we will get in the, if we follow the P curve, P cooling curve. Anyone? Others also can try to answer. Uh, it is not necessary that you have to give only right answer. At least try. Okay, 100% perlite. Yes, you are right. Because when it is this curve is touching here, that means transformation is starting. Then the transformation is progressing. Here it will form 50%, and as soon as it touches this curve, that means 100% perlitic transformation has occurred. So that gamma is transformed 100% up to 100% perlite. So now then only the different fraction of alpha or cementite may change depending on the temperature, right? So means 100, once the 100% transformation has occurred, now as you are decreasing or quenching, so that fraction of cementite and alpha may get changed, but total percentage of perlite will be 100%. So if you follow the P cooling curve, it will be 100% perlitic structure you will get. So now you can see from the S cooling curve we will get martensite plus lithium austenite. From the R we will get 50% perlite martensite plus lithium austenite. From the Q you will get 50% benite plus lithium austenite plus martensite. And in the P you will get, if we follow the P cooling curve, we will get 100% perlite. So the correct answer is option B. That is, if we follow the Q cooling curve, it will produce 50% benitic structure. So everyone understood how we are getting different fraction of phase, different morphology of phase, depending on the cooling rates. So now you can tell that what is the significance of this C curve or transformation temperature TTT curve, that is transformation temperature and time. Everyone understood?
Yes, sir.
Okay. Okay. Now I want to ask a question that how you are getting this C curve, means how you will generate this C curve experimentally, or how you will develop this C curve, that is the time, temperature and transformation, how you will get. Do you people know how to generate the C curve experimentally, how you will find out? And while the shape is C type. From the lever rule, no, not exactly, because in the lever rule you will get the fraction of the phases that are present for a certain uh, temperature. There is no relationship with the time, but in TTT curve there is a relationship with time. Isothermal annealing. If you do isothermal annealing, then yes, means you will hold at a temperature for a certain time, and then you will quench, right? So okay, let's say you took one alloy here. Let's say I'm taking this alloy only, that you take to it. Okay, let's move into the next page so it will be better. Let's say I'm taking this alloy. Okay, so now what I will in TTT diagram I have to find transformation with respect to temperature and time, right? So alloy composition, let's say you take this alloy composition, what you will do, you will take this alloy to a certain temperature, let's say T is equal to T1 temperature, you took this, and then for a certain time, that is T1, and then you will quench. So first from the, let's say from the room temperature you will go up to the T1 temperature. This is the T1 temperature, we will hold for certain time. Then let's say this is T1 time, then we will quench. So quenching means what is the microstructure formed at this holding period, that will only retain, and it may also transform to the Martin side, but that paralytic fraction that is present is given here in the CCT curve, that will not be affected, because upon quenching that paralyte will not change, right? So you will get now, let's say you did this thing for different set of time, this at the same temperature, this is one, then you hold it for T2 times, let's say this is T2, again let's say you hold it for up to T3. So same alloy, you have do the we will do the isothermal annealing at a temperature for different time interval. So what you will see that it will take some time to nucleate. So this gap is basically so incubation period. Once it is nucleate, that phase fraction. Okay, in this axis it is the fraction of the transform, and this axis is the time. So first it will take some time to nucleate. So this is time is incubation time. Then it will nucleate, and with time your fraction of transform will increase. So this is 0, and it will transform up to 100%. So let's say this part is 100%. Okay. So now this is for a single temperature, right? Now if you draw temperature in this axis and time in this axis as drawn in the CCT, so for a certain time you will get different fraction of transformation, right? So here it is 0, then you will get one point here, then you will get another point here. Okay, so this is let's say this is the 10% transformation, let's say this is 50%, and this is 100%. So corresponding to the 100%, let's say this is the temperature T1. So corresponding to the transformation, you will get 1 point here for 10%, 1 point here for 50%, 1 point here for 100%, right? Now if you do for different temperatures, right, let's say again this set of experiment you will repeat for another set of temperatures, say T2. Now in this time you will hold at T2. So let's say T2 is lower than T1, and T3 This is T2, T1, T3. Let's say T2 is lower than this temperature, and again you will get some fraction transform, but this in this case this time will required. What will be the time required is longer time, because you are uh, doing at lower temperature. So the 10% transformation, let's say it will be here in this case. Okay, so again if you do again this at T3 and T4 like this, you will get this point. So, and if you go above at the up high temperature, then also there will be a nucleation barrier. For this also this will vary. So we'll get this C type of thing. It will be C type because if you because it is controlled by both the nucleation and growth, right? So nucleation is depends on the driving force, that is how much undercooling you are giving, but growth is depends on the temperature. If you give the very much higher undercooling, then your nucleation rate will be higher, but your growth will be less, because you are doing at lower temperature, or you are holding at lower temperature. But and again if you at higher temperature, then your nucleation rate will be less, but your growth will be higher. So there is a two opposing effect is there, right? So you will get one optimum temperature where the nucleation rate will be maximum, and nucleation and growth rate will be maximum, both combination of both will be maximum. So let's say this point is this one. So as you go above this point, your nucleation rate will decrease, but growth will increase, but and overall it will decrease. And that's why your time required for the same percentage of transformation will be higher. Again if you go to the higher temperature, it will be much more higher and higher. So that's why you are getting this curve as a C type, where uh, in at a certain temperature it will be maximum or optimum, where you will get the same fraction of transformation for lesser time, but at the other temperature we will get the same fraction of transformation at higher time, longer time. So now this one C curve is for 10% transformation. Similarly, as I told that for 50% also you will get one curve. So for 50% also you will get like this one curve like this, and again for 100% transformation also we will get another curve. So this way basically C curves or TTT means transformation temperature and time. This curve is generated. Got it? Any doubt? Hello? Am I audible? Okay. Anyone has any other doubt, or want me to explain any other concept from this TTT curve and all, and or phase diagram? This question all people understood, right? Why Q is giving 50% benite? Okay. Difference between CCT and TTT. Yes, good question. So CCT means continuous cooling transformation. That is when you are cooling it continuously. TTT is transformation temperature and with time, right? So in TTT means what you will, okay. So let's go to the new okay. So let's say you have kept your this is a furnace, box furnace. You have kept your one sample. Okay. So in case of and this is another furnace, you kept your own sample. So in case of CCT, what you will do first, from the AC1 temperature, you will go to the AC1 temperature. That was given in the CCT, right? This is the CCT curve or TTT curve. So this was the AC1 temperature, above which it will be austenite. and then depending on the cooling rate, how you are getting the fraction, it will give you. Now for CCT, let's say you are at above the AC1 temperature initially, so your sample will have austenite only, right? Now to generate the CCT curve, what you have to do, you have to cool it continuously up to a certain time. Let's say I am drawing the temperature, uh, heating cycle. So initially you are at you move to the AC1, this is the AC1 temperature, then you will continuously cool it, like not quenching, continuously cool means up to it will take some time, or furnace cooling or something you are doing, right? Then you are holding at this temperature time. Means- no, in this case you are not holding, you are just continuously cooling, right? Now you can do one thing. So you cool up to this continuously cool, and then you quench it. One sample you will get from this, again you cool for a longer time and then you quench it, again you cool for a further longer time and then you quench it. So at these three, let's say three different time you quench, T1, T2, T3. So this is the CCT. So again this generation of the curve will be same as I have explained here, but the your heating cycle will be different. Sorry. So in case of CCT, you are continuously cooling. But in case of TTT, what you will do, you will hold that, you will go to the AC1 temperature. Let's say you went to the AC1 temperature for certain time. Then you will quench at temperature T1 and hold it for some time. Then you will quench it again. Then again what you will do, you will quench up to temperature T2 and then hold for some time and then you quench it. Then and at T3, then you quench. Let's say this is T1, T2, T3. Okay. Similarly, you can also quench at further lower temperature and then you quench, right? So in TTT, what you are doing, you are just suddenly quenching your sample to a some temperature and then you are holding at this point. So that means what is happening? You are giving us a certain time at the same temperature, means at a constant temperature you are giving, allowing some time to form the phase. But here what you are doing, the temperature is continuously decreasing, right? You are not quenching, it is continuously decreasing by furnace cooling or like this. So in this case what you are doing, you are not allowing at this temperature for sometimes you are just directly quenching it. So up to this time, it is this the fraction formed at this point, it is not because of this temperature only, it is because the accumulation of this continuous transformation over this temperature range, and then you are cooling it, right? So in this case at a certain time you are not allowing, at constant t you are not allowing to form phase or for transformation. So in this case you are not allowing uh, uh, for the transformation. So in this case what will happen, that your CCT curve or will shift towards the right, like if it is a TTT curve, and let's say this CCT curve will shift towards right, because you are continuously decreasing the temperature, so it will take longer time to form the same fraction. Got it? Because you are giving it some times to form the phase. Here you are not giving some time, you are continuously decreasing the temperature and certain time you are quenching it and then you are checking what is the fraction is transformed. So that is the way your CCT curve will be a bit right side to that of the TTT curve. Understood? Yes. Okay. Basically, in reality, we follow the CCT curve only most of the time, because mostly we do deal with the continuous cooling and these things. And we also sometimes follow the TTT curve when we do the aging treatment or heat treatment. So in this aging treatment, we follow the TTT curve. Any other question? Everyone is okay with this? Okay. Okay, then if no one has any doubt, then we'll close for today and we'll meet in the next Friday again to solve the other questions. Okay, okay then. Okay, see you all in the next Friday then.